Okay, so with Riemann sums, hopefully you're getting the idea. We got lots of notes, so let's get rolling. So the table of values gives the function from experiment. Use them to estimate that integral with a left Riemann sum. Well, just like yesterday, the first thing we're going to do is the width, and that width is the difference of the bounds divided by the number of sum intervals I have. So that width will be 2. Now, I'm not saying I necessarily draw a full picture, but y'all, I do this. I go, okay, I'm going from 0 to 6. I see my rectangles taking shape. Now, what side of them is going to be on the function? Well, if it said a left sum, that means whatever my graph is doing, okay, and your graph doesn't have to be, whatever, it's going to the negatives, but you don't even have to be that specific. 0, the left sum is going to be there. 2 and 4. What you have to realize are the only numbers on the chart that you're looking at are these 3. And I don't even bother writing the f of. Once I understand that, I just say, okay, this integral is going to be approximately, do I have a common width? Yep, so I'll pull that out. And what are my 3 heights? Well, my 3 heights are going to be f of 0, but you can't leave it as f of 0. If they have a chart, they want you to read the numbers off of the chart. So I want to make sure I copy those down, and then that's just a matter of typing it in, and you get 39.8. It's a very quick problem. Again, I didn't do that in my head. I did that on a calculator or whatever. So you can definitely have a calculator on this one. So now we have another word problem. It says use a right Riemann sum. You can read that. Table gives the values of the rate in gallons per second in which water flowed into a lake with readings taken at specific times. Use a right Riemann sum with 5 subintervals indicated by the table. Now this is an important one. I am going to draw this one out. We have rate in gallons per second, and we have time. Now I say I'm going to draw it out. I'm going to draw it out very quickly because you don't want to waste the time to be that careful. My function is decreasing, so I'll just, good enough. Now look at my 5 subintervals and notice that it didn't say the word equal. Here are my 5 rectangles. Do you see them? 1, 2, 1, 2, 3, 4, 5 taking shape. Now I'm doing a right sum, so the right upper corner is on your graph. So you kind of go, all right, I have 6 values. What 5 are going to be important to me are going to be those 5 if I'm using a right sum. But here's what I need you to hugely star. When I do this one, notice that I'm not doing a width where I go 60 minus 0 divided by 5. Friends, it didn't say the word equal widths. It says subintervals indicated by the data in the table. So when you're going for the width of this box, this first box, what is the width of that box? That width is 10. What is the width of this box? That's 15. So you cannot, that's what it means by indicated by the table. The widths aren't the same. So if there are not equal widths, you can't pull out a common width if it's not common. Okay? So you cannot pull out a common width. Because there isn't a common one. So you have to do this integral from 0 to 60 of your function. I'm just going to call rate, I'll just call that r of t. People, you have to do it separately. Okay? You have to literally look at each individual rectangle. It's the area of rectangles. Okay, people in 5th grade can do area of rectangle, so I know that you sweet children can too. What is your base? 10. What is the height? Well, it would be whatever this value is, and that is 400. Look at the next rectangle. What is the base? Well, 25, 10 to 25, that's 15. And what is the height right here? Well, that's going to be 350. If you will draw it, you will get it right. What is the width right here? 12. And then you're going to use 280. And so you kind of get the idea. And so some people go, oh, okay. So I know that my widths are going to be the difference in these values, which is totally correct. And they kind of get the system, and they're able just to, write it and rock it. So 200 and then 14 and 180. And when you get that, what you get is you get 16,930 gallons. Remember, if you go, how do you know it's gallons? Well, estimate the total amount of water. That's going to be in gallons. But remember, when you're doing the area under the curve, you multiply the units together. So if I'm doing gallons per second times second, when you're integrating, notice that I get gallons. So that's what you got. All right, let's look at this next one. And this one is a wonderful, this was an AP question. I don't remember what year it was, but it has all the parts. And so here we go. It says, given the rate of fuel consumption in gallons per minute recorded during an airplane flight is given by a twice differentiable. That's important. Means you can take the derivative, it's never undefined, and strictly increasing. They probably told you that for a reason. The graph of R and the table of selected values of R at the time interval in minutes are shown. Now, I always, when I'm on AP, y'all, you're either going to be doing derivatives or integrals, most likely. I kind of think if I'm doing the integral, gallons per minute times minute, if I did the area under the curve, what is that going to give me? That gives me gallons. I just kind of know that. I go, okay, so the area under the curve would give me gallons. That would be the amount of fuel I used. All right, good to know. Let's go on. Using the data from the table, find an approximation for R prime of 45. Remember me telling you it's on the AP test every year? Here it is, and you're going to get the 2 points. It's giving you, this is R of t. It's asking for you to approximate the derivative at 45. Approximately, what is this? You know what to do. You're going to find the points around that, and you're going to say you're going to label R prime of 45 is approximately, you're going to take the 2 points around it and find the slope. 55 minus 40, and you're going to write down slope, even though you can do it in your head. You're going to write down that difference quotient because that is 1 point. And then the other point is going to be your answer. That's 15 over 10. Obviously, you can write the answer in many different ways. That's a pretty easy one, so I'm going to put 1.5. Now it says indicate units of measure, which means if you don't write that down, then the answer point you're not going to get. Now let's think about what the units would be. This was the difference in R's. So what were the units for R's? That was gallons per minute. This was the difference in time. So you divided by minutes. So gallons per minute, remember dividing by minutes is like multiplying by 1 over minutes. So my units would be gallons per minute squared. Okay, remember, 1 point for writing down the difference quotient, 1 point for that. That would be your 2 points that you sweet children are going to get. Now, letter B. I'm going to keep my picture here, but you can kind of flip your paper over. It says that The rate of fuel consumption is increasing fastest at t equals 45. What is the value of r double prime of 45? Okay, so what did they tell you? They said r prime, the rate of fuel consumption, this, is increasing the fastest. So in other words, r prime of t has its biggest value right here, okay, which kind of makes sense if you look at it. When would that derivative be the steepest? And that looks about right. So let's think about what we know. Whoa, how did I get those answers already? There we go, they disappeared. So think about what that means. If r of t, if it's increasing at the fastest rate, that means that it's the greatest value on r prime of t. At 45, the highest point, if I were to graph the derivative, r prime, it's the greatest. So that's kind of my thought process. So if r prime of t is greatest at 45, what does that mean? It means then there is a max, a local max on r prime of t at t equals 45. Okay, what did the question ask me for? The question asked me for r double prime of 45. So if there's a max, if there is a max on a function, tell me what has to be true of its derivative. Okay, I mean, they're asking for a value. Well, if there is a maximum, well, then the derivative of at that point would have to either be 0 or undefined, but they told you it's twice differentiable, which means it can't be undefined. So if there is a local max on r prime of t at 45, then r double prime of 45 would have to equal 0. And that's what they would be looking for. Okay. Letter C, approximate the value of the integral. And you're using a left sum with 5 sub-intervals. And so I'm going to go back to my picture. So let me kind of use this. So I'm doing a left sum with 5 sub-intervals. It does not say equal, so I'm not going to figure out a width because I can't. It's going to be as deemed by the table. So let me erase this. So my sub-intervals, again, here's 30. So that's going to be one rectangle. 40, 50, 70, and 100. So notice my rectangles taking shape. It said 5, correct? So 1, 2, 3, 4, 5. We were doing a left sum. So the left upper corner is going to be on f of x. Got a little crooked there. There are my 5, and I'm doing the area of those 5 rectangles. If you draw, you're going to get it right. Base times height. What is the base of this first rectangle? I'm going to kind of draw it, and then I'll turn and write it down. That would be 30. What is the height of that rectangle? Well, I'm doing a left sum, so it would be the left. I'm going to use this. Y'all, 1, 2, 3, 4, 5, 6 values. If you're doing a left sum, you're using the 5 ones on the left. So the y values that I'm going to use are those 5s. Those 5. Now, what are the bases of each of these rectangles? Wouldn't that be the difference between the two? So from 30 to 40, I probably did that 30 in the wrong spot, maybe. Sorry about that. Those numbers are a little off there, but whatever. You get the idea. So from 30 to 40, this difference was 30. So that base was 30. From 30 to 40, that base would be 10, 10. I'm not going to redraw, but I think you get the idea. And 30. Those numbers are a little off. So these are going to be my widths, and then these are going to be the matching heights. So when I go to do the Riemann sum, I'm going to write, I label everything, the integral from 0 to 100 of r of t dt is approximately, I had 30 times 20. You do need to write this down. I would suggest not. I know that you can do that multiplication in your head. For a Riemann sum, I would show them that you are doing base times height, base times height. So I would steer away from doing multiplication in your head the first time. And what does that give you? Again, technically you could leave it like that. Again, if this is on multiple choice and you had to get a number, it ends up being 4,350. Always label the units. We talked about if you integrate, you multiply the units, and we figured out that that was gallons. Now, I have to make sure I answer both questions. Is this numerical approximation less than the actual value? Explain your reasoning. What is that dependent on? Well, it depends if you have a increasing or decreasing function. Y'all, we had an increasing function. So if you looked at our table, our function was increasing. I'm using the lower 5. So I would say since r of t is increasing, the left sum will, and I'm going to use the wording, I mean, yes, is this saying is it an underestimate? Yes. Is the numerical approximation less than the actual value? I'm just going to use the wording that they used. The left sum will be less than the actual value of the integral. So I like to use the wording that they have in the problem. All right. We have 2 more. For B going from 0 to 100 minutes, explain the meaning of 0 to B in terms of the fuel consumption for the plane. Okay. Well, let's remember this. If you are explaining, okay, let's just write this down because it's the first time we're doing this. When explaining, you need 3 things. You need what it is, what you're talking about, and y'all, be specific to the problem. Okay, don't tell me area under the curve. Don't tell me that's not what they want. They want, in terms of the problem, what are you talking about? You have to provide units, and you have to do a specific time interval. So let's talk about this. And we kind of already did the first part. Remember, you're going to stop at the period. It says, explain the meaning of 0 to B R of t in terms of fuel consumption for the plane. Talk like you're talking to a 12-year-old. This integral, what would that be? Notice it says 0 to B. What would it be? It is the total amount of fuel that's consumed by the plane. Okay? Now, I'm going to kind of put that in there. It's the total amount of fuel units. Remember we talked about if we did that we get gallons. So R of T is a total amount of fuel in gallons consumed specific time interval. Don't tell me in B minutes from T equals 0 to T equals B minutes. You need to be specific with it. Now, what would happen if I took that? Think about what this is. You're like, I don't know. You just told me that that was the total amount of fuel consumed. If I divide by B, which was the number of minutes, well, figure out the units first. This was gallons, and you're dividing by B, which is minutes, so the units would be gallons per minute. Well, what would that give you? Well, that would give you kind of the average. It's like your total number of points you got on a test divided by the number of tests you took. Well, it gives you the average. So this 0 to B of R of T is the average gallons per minute. There are my units. The average gallons per minute consumed from T equals 0 to T equals B minutes. I have the total amount of gallons. I'm dividing by the number of minutes, so it's the average gallons per minute consumed from T equals 0 to B minutes. Okay, nowhere did I say that, oh, this integral is the area under the curve. That is never going to be the right answer. You talk about what it is in the specific problem that you have. All right, last one. Oh, goodness. For T being 0 to 100, does there have to be a time when R of T equals 0.5? Oh, goodness. What should we think about? You're proving the existence of something. You have R of T, and it's asking for, prove to me that the derivative has to be this particular value. What should you be thinking of? Oh, I hope that you're thinking of the MVT. They throw those theorems in there. So you have to ask yourself, does the MVT apply? Well, what are the two conditions of the MVT for derivatives? Okay, the two conditions are that the function must be continuous on the closed and differentiable on the open. Do you remember back at the very beginning of the problem, way back when it talked about that the function was twice differentiable? Okay, well, here we go. Do you have to write down the conditions? Yes, since, notice I'm using the function, since R of T is continuous on the close, 0 to 100, and differentiable on the open, then what does the MVT state? Okay. Now, again, do you have to write the words MVT? No, you do not. So you don't have to state it, but remember what the MVT says. It says that, let me just draw some funky picture. If you have the slope of the tangent line here, I promise you there has to be a value within the interval that the tangent line or the derivative is equal to that slope of the secant line. So the slope of the tangent line has to equal the slope of the tangent line. So I'll say it like this, and since R of T is and differentiable on that, there must be a C in the interval from 0 to 100 such that what? Well, f prime of C would have to equal, I'm going to write this out, the difference of the y's over the difference of the x's. Now let's see what I get for that. I'm going back to the chart. If I go back to the chart, where's my chart? Okay, what am I looking at on this chart? Let me erase this. I'm looking at this and finding the slope. So the difference in the y's would be 70 minus 20, and the difference in the x's is, of course, 100 minus 0. Not that I do that in my head, but I write it down. So 70 minus 20 over 100 minus 0. Well, lo and behold, look what I get. I get 0.5. So it says there must be a value. Okay, now notice I need to be, I did it this way because I was kind of stating the mean value theorem. So I'd probably restate, because that says for t being 0 to 100, I could certainly change those to t's. And that'd probably be the fastest thing to do. I need to have a variable match up. So I'm going to change those. There must be a t in 0 to 100 such that f prime of t is that. So, well, see, I need to change this too. You got to have your variables matching up. So that's something to kind of check for, that you kind of rattle off the mean value theorem with C's and F's because that's what we learned. But after you do it, look back at your wording and make sure that you're using the variables from the problem and do a little erasing and changing to make it match up. And so that's what I have. So yes, there must be a value of t between 0 and 100 that the derivative equals 0.5. All right, so wonderful, wonderful free responses. You know there's going to be a free response part on this test. That was great examples of what a free response would look like. So work on that and peace out.